Okay, so good afternoon, everyone. So I hope I'm audible. So please let me know if I'm audible so that we can start the session. Okay, so any one of you can please let me know if I'm audible. Okay, great. So I think then we can go ahead. So as you know, today we're going to discuss some of the good quality questions from machine design portion for your upcoming exams, right? That you already know, your BHEL and HPCL. So we'll be discussing on those lines. Okay, so keep responding while we will be discussing the questions. So keep responding over there, so that will be a fruitful session that way, right? Okay, so let's go ahead. So here's the first question. So just please go ahead and keep giving your answers also simultaneously. Okay, so it says the ratio of maximum stress in a machine component at a notch or fillet to the nominal stress at the same section is called. What is the name given to it? Okay. So, okay, I know that almost all of you may be able to answer this particular question, but just I want to give one clarification, that's all. So just keep it in mind that, okay, when we define the stress concentration factor, you say this is the maximum value of the stress divided by the nominal value of the stress. So just keep it in mind, this nominal value of stress is also the maximum value of stress. It is also the maximum value of stress, but this maximum value of the stress is based upon the formula. You don't have formula to calculate this maximum value of the stress when you are introducing any particular notch. So if I ask you calculate the value of this maximum stress that is induced over here at the notch section, that is induced here at the notch section, taking into account this discontinuity, you don't have any formula. The only formula that you have is this one, to calculate the maximum value of the stress at that discontinuity. And if I ask you what is the maximum value of the stress at discontinuity, then you will say that, say if this is a smaller diameter, this is a larger diameter, then obviously you're going to say that this is a smaller diameter, so smallest cross section area is this one. So you say this maximum value of the stress as per the formula will be equal to what? P divided by, let's say if you're applying load P, pi by 4 minimum cross sectional area, this one. So just keep it in mind, both the values are the maximum value of the stress. One is the actual value of maximum stress taking into account the discontinuity. The other one is based upon the formula that you are regularly using, right? That is how it is that you need to know. So this ratio we call it as a stress concentration factor. Go to this one. Okay, the resistance to the fatigue of a material is measured by, right? So how do you measure that means what is the criteria? Basically the question is this way, that what is the criteria of failure in case of when a component is subjected to fluctuating stresses or when it is subjected to a fatigue loading, right? So obviously, because if you see all other options, the most probable option is endurance limit. It will depend upon the situation. For example, endurance limit is the criteria when you are subjecting that component to the completely reverse stresses, right? This SN diagram that we have is only for the completely, this is a log graph, this diagram. So this is for the completely reverse stresses. So if I have to design the component for the fatigue failure, in the fatigue failure, when it is subjected to completely reverse stresses, then obviously, this becomes the endurance limit. This is the maximum value of the stress amplitude. We denote it with this one. Notation could be different. So that this material can carry for unlimited number of stress cycles. Same way, if you want to design the component for fatigue loading, provided it is subjected to the fluctuating stresses, not the completely reverse stresses, then you are having the Soderberg, Goodman, and Gerber criteria. So since he's not talking about any other thing, so we understand that he's talking about only that, okay, since he has mentioned endurance limit, so endurance limit is only criteria when it is subject to completely reverse stresses, and this is also a case of fatigue loading. Simple. Go ahead. So a screw thread is defined by its what? Now keep it in mind, he's talking about the screw thread. But that means he's not making distinction in terms of internal and external. So obviously screw thread means screw for us. It's a kind of bolt for us, right? So screw thread, this is a screw thread. Let's say this is a screw. It could be a screw or bolt. You know the difference. Let's say if I say this is a screw, okay. Something I should have drawn it a little larger to make it look. Right? Let's say this is a screw. Right? So screw thread is defined by its what? Which diameter is this? The largest diameter, or we also call it as a nominal diameter. And in this case, it is the what? Nominal diameter or largest diameter, and these are the crest. This is crest portion. So I can also call it as a crest diameter, crest to crest diameter also. So it is defined by its nominal diameter. And you also know it is also, if it is a fine thread, then we also mention the pitch also in the metric isometric threads. For example, we mention it like, let's say 50 into 1.5. So this becomes the nominal diameter. It's a coarse thread, then we simply say, okay, M, let us say 50. So metric threads, nominal diameter in mm. So in this case, since he's not talking about this, whether it's a fine or coarse, so for us, we think that, okay, this may be the specification he's talking about, because pitch is not mentioned. So when I have to define the screw thread, so we will define it by its nominal diameter. And if he's talking about the fine threads, then obviously you have to go for the pitch also. But anyway, he's not mentioned, so we are not talking about this. So it means out of this, which one is core diameter is the smallest? Core and root is same. This core and root. That means he's talking about this in both the cases. Pitch diameter, obviously, you know, somewhere here. And then you are left out with the crest diameter. This is the largest diameter of the nominal diameter. So we are going to define it with the which one? Which one? That is a D. Okay. Let's go ahead. Go through this question and try to answer. Then we'll discuss. Stresses in the welded joints are difficult to determine because of the following variables and unpredictable parameters, except that means you have to find out the parameter which is not responsible for this difficulty. Okay, so even if you see, sometimes there are going to be some questions over there where even if you don't know the other options, you don't have much clarity of all the options, even then you will come to the conclusion. That also look for those possibilities in the examination hall, right? So for example, as some of you just answered C, size of the electrode, how is it related to stresses in the welded joints? It looks a little weird that determination of the stresses in the welded joints somehow could be related to the size of the electrode. It is very difficult to, even if you're common that knowledge that you have, whatever the basic knowledge that you have, based upon that, it becomes difficult for you to analyze, right? So my point is that even if you are not very clear about this and other points, then also it will something look weird for you that, okay, this, how it is related to the difficulty of determining the stresses in the welded joint, if size of and how it is related to the size of the electrode, right? So now let's see one by one. Okay, so it means all other parameters are somehow related to the stresses in the welded portion. For example, stresses in the welded joints are difficult to determine because of the following variables and unpredictable parameters. What could be those? Homogeneity of the weld material. That means weld portion or weld material, that portion is not homogeneous throughout. You'll have difficulty to find out the stresses, because for finding out the stresses, you need to consider that material as a rather you have done the basic assumption in strength of material that material should be homogeneous and isotropic. It makes your life easier in terms of finding out the stresses. But if it is not homogeneous, you are putting yourself in difficulty because you are going to have the variation in the properties. And if variational properties are over there, you're going to face a problem in finding out the values. Thermal stress is in the weld, obviously, because in different portions of weld zone we call heat affected welded zone. In that case, you could have the thermal stresses also. I need to take into account thermal stresses effects also, the structural changes that are taking place over there. So all these factors make the things complicated with respect to the stresses. Change in physical parameters due to the high rate of cooling, obviously. So cooling rate is different. Structural changes will take place within the weld material, and therefore, so all these parameters, they influence the how we are going to find out the stresses or make the things difficult for us to determine the stresses in the weld portion. But it is not related to the size of electrode, right? It is small or larger, because size of electrode we have to do with respect to the how much that thickness of the plate is and all that that we have to weld, but not related to the how much stresses will be developed. So that is how you have to see. So sometimes if there is no very good clarity on the options, you can go by the elimination approach also, and maybe sometimes common sense may also work. Okay, go ahead. Oh, C was the answer. Charan, last question, C was the answer. That is it does not depends upon the size of the weld electrode. Okay, go to this one. Bolts of uniform strength. For the bolts of uniform strength, the shank diameter is made equal to this is the normal bolt. Okay, this is the normal bolt that you have. Let's say, right? So if I ask you, if I am putting it into the pulling force, applying the pulling force, let's say, so if I ask you where is going to be the maximum value of the stress, you will say the maximum value of stress is going to be at the minimum cross sectional area, and minimum cross sectional area is the core diameter. Whereas this diameter is larger because this is a nominal diameter, right? This is the largest diameter. So it means in this case, if you see at the threaded portion, you are going to have the larger stress, whereas in this portion, you're going to have the less stress. And obviously, you will take the value of core diameter such that it carries that particular load. आप core diameter उतना लोगे so that whatever the load that you have, design load, it must be able to carry, core diameter must be able to carry that load. So let's say you have decided that 20 mm is the core diameter for a particular load 10 kilonewton that you are applying. Maximum load that you're going to apply is 10 kilonewton. Corresponding to that, you need a core diameter of this one. Now, if I ask you, if this is 20 mm and this diameter is larger, obviously because this is a larger diameter, and if I take 30, hypothetically, then obviously the stress induced over here will be less than this one. So why should I provide the additional material over here when I have sufficient material taken at the core section which can sustain this load? It means 20 mm diameter, core diameter can sustain this much load. So taking the larger diameter over here carries no meaning, because even if I reduce this diameter to a smaller diameter, let's say if I make it smaller now, smaller means equal to this one, the core smaller to core diameter, that means smaller, that means equal to core diameter. So now this is also 20. So if I tell you where you're going to have the maximum stress, you will say at the smallest section, and smallest section is this one, and 20 mm is able to carry 10 kilonewton. Then if I'm making it 20 mm, this will also be able to carry that 10 kilonewton. So where is the trouble? So what I did is, instead of taking it as a 30 mm, which I was earlier taking as the largest, which was, so I'm saving this much material. It has the same, if you try to relate the things, you can relate the things with respect to beam of uniform strength that you study. Just a minute. Okay. Just a minute. Right. So you can compare this logic with the same thing that you have in beam of uniform strength in strength of material. Why you make that beam of uniform strength? To save the material. You are saving the material. Every section is subjected to its maximum permissible limits. That's what I want. Every section should be subjected to a load to its maximum carrying capacity. तो अगर ये इसको इतना इसको carry कर सकता, this, let's say this is the maximum 20. So obviously why should I unnecessarily provide this additional material, this one? So I'm saving this material. So what I will do, I will reduce this bolts of uniform strength. The shank diameter, this is a shank portion, as you know, is made equal to what? The core diameter. I have made it equal to the core diameter. Now at any section, when I will calculate the maximum value of stress, it will be same. So minor diameter of the threads. This is a minor or smaller diameter. Core diameter, major, pitch, no, nominal and major is same. They are same. Pitch is also larger than the minor diameter. So you are left out with C option. Okay, so let's go to the next one. This is, I think, will be easy for you to answer. In a fillet welded joint, the weakest area of the weld is this fillet weld. Fillet weld, आपको पता है? This is the fillet weld. And when we talk about the fillet weld, let's say even if it is on that side also, so the weakest area or the weakest section is the throat section, which is when I drop perpendicular from here to on this particular this one. This section is the smallest section you can think of. Other sections are going to larger one. Let's say, for example, if I take it this one, so this length will be more than this. So when I will take any line coming out from this intersection, that will be larger than this throat one. All these, they will be larger than this one. So this is the throat section over here. Go ahead with this one. Just keep it in mind, we have this and this is Gerber, this is Goodman, and this is Soderbergh. So design calculation for members subject to fluctuating loads with same factor of safety yields the more conservative estimates when using. See, point is you have to see which one is more conservative for design purposes over here. We say that Soderbergh basically is the most conservative design criteria when we are talking about the fluctuating stresses, components getting subjected to fluctuating stresses, right? Why we say so? That because this is a little, I think, better. It will be something this way, okay? Gerber is this one. So actual basically failure points, they are not over here, but actual failure points are something this way. So deliberately I have shown you these points, but this is how the things are. if you know, these are the failure points, right? Actual failure point. This is how the distribution of the failure points will be when you carry out the testing, and then these investigators use their own approaches to join these points. Soderbergh used this approach, Goodman used this approach, Gerber used this approach. Now, if I ask you, which one out of all these goes through maximum failure points? Which line or curve out of all these goes through most failure points? You will say, of course, it looks like that Gerber curve. It looks like that Gerber curve is passing through most of the failure points. Soderbergh, see, failure points are far away, and still there are a few random points which are over here. So still he took this particular line, joining these points. Then if you see Goodman was little better in joining these curves. Okay, it's little better than Soderbergh. So that way, if you see, Soderbergh played very safe. Even though when I am subjecting the component to the mean value of stress, let us say this one, and amplitude of stress, let us say something, this one, let's say I will call, as you know, this graph is for stress amplitude. On this axis you are having stress amplitude, on this axis you are having mean value of stress. I hope you know that. So let us say if I am taking any value of amplitude, so you are subjecting the component to a stress amplitude of this one and mean value of this one. Now if I extend them, actual that component failed somewhere here. Actual that component failed somewhere. It will fail beyond that value, but okay, this becomes a limiting point. But what as per Soderbergh? As per the Soderbergh, this point, the failure must have taken beyond this, well below this combination, well below the combination of this one, because limiting value lies on this particular line only. So it means you are playing very safe. You are taking the failure at a very low value, whereas actually the failure will take place at a some higher value of stress, combination of stress amplitude and mean value of stress, right? So that is why we are saying this is the most conservative. Now, when we are saying that he's playing safe, that means we are saying he's very conservative. Gerber, least conservative, because he's going through almost maximum failure points. Now, if he is most conservative, then obviously, even if you are applying the factor of safety, same value of factor of safety. So if I am applying the factor of safety on this line, then I will come over here and I will have this line somewhere here. I will join that line. So you are having same way on this line. I will apply same value of factor of safety. Same factor of safety I apply over here. So I will come over here. So again, this line will be something this way, parallel to this line. So it means even if I apply the same factor of safety, it is not that Soderbergh is going to be less conservative. He is going to remain the same situation is going to happen, because factor of safety in any case I have to apply. So that is why if you say design calculation for members subjected to fluctuating load with the same factor of safety, that means same factor of safety whether I apply on this criteria, on this criteria, on this criteria. So since I'm applying the same factor of safety on all these criteria, and since Soderbergh is the most conservative, he is going to remain the conservative even after applying the same value of factor of safety. That is the meaning of this. So it means the correct option is going to be Soderbergh. Okay. Go ahead. Consider the following statements. Stress concentration factors are used for ductile materials under static loading. Stress concentration factors are used for brittle materials under static. Okay. So, you know, let's say we say that you are having a component in which you are going to have the discontinuity. So we say that, okay, you're going to have a larger value of stress over here. But what happens is, should we use the value of stress concentration? That means maximum value of stress to the maximum value of stress as per the formula, nominal value of stress KT. Should I use KT or not? That is a question over here. So if provided this is a static loading case, and material is ductile or brittle. Let's say if it is ductile, so normally what happens is when there is a discontinuity, stress will concentrate over here, but because of the stress concentration, local yielding will take place, because these materials can yield locally. So if local yielding will take place, so because of that, this sharp discontinuity as of now, let us say, it will not remain sharp. Why? Because yielding will take place over here. When yielding will take place, then this shape will change and something, it will become this one. This shape will change and it will become smooth. So the effect of stress concentration will decrease, and therefore we say that we don't need to use the stress concentration ductile materials because of the ductility. Material yields locally and stress redistribution will take place, and therefore we say that this will become equal to 1. It means, what is the meaning of this? It means for ductile materials, actual value of maximum stress will become equal to the maximum value of the stress that you have calculated as per the formula. They are going to have the same. So you don't need to use the KT. Simply calculate the maximum value of stress that you calculate as per your regular practice, as per your regular formula. That's all, and that becomes your actual value of maximum stress. Also, the job is done. And but in case of brittle material, this is not the case, because this yielding will not take place. When yielding will not take place, redistribution means the actual value of maximum stress will get decreased. So that will not happen. So what is going to happen? Brittle material, they don't yield. Sharp discontinuity. They can fracture, but they cannot yield. So if they don't yield, it means stress concentration. In ductile materials, initially stress, because of the stress concentration, actual value of stress increased. But because that actual value of stress increased, that increased value of stress basically yielded the material, and then stress redistribution took place. Net effect at the end, no stress concentration. Nearly, that means it got reduced. But here, that is not happening. Stress concentration is happening, but it is not able to redistribute that stress, and therefore we need to use the some value of stress concentration factor over here in case of brittle materials. It means for brittle materials, actual value of maximum stress will definitely be greater than the maximum value of the stress that you calculate as per the formula. That's the meaning of this. So that is why stress concentration are used for ductile material under static loading. It becomes wrong, right? Are used for ductile. No, you don't use, right? So this is wrong. Which one is? Are used for brittle materials. That means which one of these following statements are correct? Basically, that should have been the statement. But anyway, so 2 is the only correct statement because you use in static loading, right? But if I frame the question now, do you use the stress concentration factor in ductile and brittle materials in case of dynamic loading? Of course you use, because in both the cases, in whether it is a ductile or brittle, both the materials behave in the same way. In dynamic loading, in static loading, they are behaving different way. One is yielding, other is not yielding. But in dynamic loading, both the materials are behaving same way through development of crack. So therefore, since yielding is not taking place in case of ductile materials in dynamic loading, so they are behaving like a brittle material. So in both the cases, we are going to use the stress concentration factor. There we use the stress concentration factor, as you know, we call that stress concentration factor as fatigue stress concentration factor rather than the theoretical KT stress concentration factor. Go ahead. Okay, this question, these questions are framed this way. I have not written other statements. What you need to identify is whether statement 1 is correct, whether statement 2 is correct, or both are correct. Or if both are correct, this is the correct explanation for first one. So that you need to check. First, check whether both are correct. If both are correct, then find out whether this is correctly explaining this one. That means this is the correct explanation. Second statement is the correct explanation for the first statement. That you have to find out. Okay, so what I'm doing is, this one. Now what I'm doing is the same component or this one I'm subjecting to this one. Right? So what he says, the endurance limit in an axial loading, this one. Endurance limit will come into picture, completely reverse axial load, completely reverse bending load is lower than that of reverse bending. बोलता है इस केस में let us say ये वैल्यू है and इस केस में क्या हो रहा है, ये वैल्यू कम हो रही है. This is lower than compared to this one. So is it the case? Endurance limit axial loading is lower than in the reverse bending. Okay, this statement is correct. Even if you don't know, let's say consider it correct as of now, because this is correct statement. So we want to see whether that next statement is correct and correctly explains the logic for this. Possibility of micro crack being present under high stress in axial loading is higher than that of the reverse bending. ये बोलता है because there is higher possibility. Keep it in mind, the size is same size I am not changing. Whatever the size, this one, this and this size is same. They are same, right? Same size. So if it is, I'm just writing it this way, right? Size, let's say if I am taking diameter, its diameter is same. That's it. Okay. So if the size is same, everything is same, then he says that possibility of the micro crack being present over here under high stresses in axial loading is higher compared to this one. Basically, this statement is also correct. And also, since this is correct, this is also correctly explaining that is logic for the first one. What is the meaning of that? Meaning is that, see, when you are subjected to completely reverse bending, actually, maximum value of stress is taking place on the periphery, at the center 0. If you are completely reversing, then obviously what is happening is top and bottom. So it means this whole of the top layer, this one, all these points at the top, there and at all the points at the bottom, let's say. Or if you are rotating it, because you have calculated it based upon the that rotating beam specimen, even if you are rotating it, that means only the periphery portion, top fiber, all the points on the top fiber are subjected to completely reverse stresses of highest magnitude. Even you can say that, okay, bending stresses are there also at the layer if you are taking, because y distance if you will decrease, so it is only the middle layer, neutral axis there where bending stresses are 0. But cyclic nature is going to be at these points also, at any point over here also, at the somewhere down there over here. But the maximum value of the stress is only at the periphery, and that is fluctuating. Think of the situation over here. Here, the maximum value of the stress is not only on the periphery, but the maximum value of stress is also at all the points on this whole of this cross section, because you are applying the force this way. So this force is acting on all the points over there. So maximum value of stress is getting applied in all the points throughout the component at any particular cross section if you take. But same is not the situation over here, because it is only at periphery. Maximum value is only at periphery. It means the possibility that the micro crack, obviously micro crack may exist over here also, but possibility that micro crack which is existing over here is getting subjected to maximum value of stress over here is more compared to here. Because why? Because the whole of the cross sectional area is getting subjected to that particular maximum value of stress. And that is why, because let's say had it been a case you are having micro crack over here somewhere inside, but it is getting subjected to lesser value of stress. So endurance limit, it is not influencing the endurance limit by that much amount. But over here, let's say you are having a crack inside somewhere inside. Now, since that crack is getting subjected to a maximum value of the stress, it means it is going to influence your endurance limit. That is the maximum value of the stress that it can carry before failure will go down, because stress concentration will take place, which will reduce its ability to carry that maximum load. So that is why you will say why that in axial loading, first is that this one endurance limit is going to be lesser compared to this one. And why? Because larger area is getting subjected to the maximum value of the stress, and there is higher possibility, because if there is any crack, that will be subjected to the maximum value of stress and therefore overall value of the endurance strength, its ability to carry the maximum value of the maximum amplitude of the stress will decrease. So that is how. So this correct. So you can say both are correct, and this is the correct explanation for first one. I hope you understood it. Go ahead. Which one of falling is not an advantage of welded joints? Over riveted joints. थोड़ा ढंग से सोचना इसको. आंसर आपके पास है. You all have the answer. You will be able to answer. That's what I understand. But अगर ढंग से थोड़ा सोचो, पहले ये देख लो, just see कि which one are the advantages, which one of the following are the advantages of welded joint over riveted joint. अगर इस तरीके से सोच के करोगे थोड़ा आंसर आपका सही आएगा कि इनमें से तीन ऐसी होंगी. There are going to be three choices which are the advantages of welded joints over riveted joints. So first identify those three advantages which are over the of the welded joints which are over riveted joints. उनको आइडेंटिफाई कर लो. बच गई जो है दैट इज डिसएडवांटेज. right now you came to the right conclusion. Yes, so you have to think about this question. तो जब भी आपको ऐसा कंफ्यूजन आए, देखो अब आपने सबने मॉडिफाई करना शुरू किया. ऑल ऑफ यू स्टार्टेड मॉडिफाइंग योर आंसर्स. अर्लियर यू वर आंसरिंग समथिंग एल्स, नाउ यू आर आंसरिंग समथिंग एल्स. सो राइट, अब आपका आंसर सही है. सी व्हेन यू गेट कंफ्यूज्ड, इस तरह की स्टेटमेंट में जब भी व्हेनेवर यू गेट कंफ्यूज्ड, नॉट एन एडवांटेज, सो व्हाट इज, तो disadvantage. Which one of the following is not an advantage? That means he's asking you which is the disadvantage of welded joint over riveted joints. Or indirectly, there are going to be three options. He's asking the one disadvantage. So he's asking you that you just identify three advantages of welded joint. So there are going to be three advantages of welded joints over riveted joints on this option. So okay, let's come to this. So assembly is lighter and less costly. So is it advantage of welded joint over riveted joints? Of course, assembly is lighter because in riveted joint you are going to use the rivets, their heads and all that. Even some cases straps you are going to use. So riveted joints are heavier and costly because you are using double strap butt joint, single strap butt joint, right? What are those? Additional strap you are using. So it means this is the advantage. So I have to remove the advantages. Now, tight and leak proof assembly. Of course, welded joints, you can consider the welded joints more leak proof than the riveted joints. So riveted joint, you have to use the different combination to make them more leak proof. Or to make the flue tight joints, you need to use the different patterns of the riveted joints. So it means this is also an advantage of welded joint over riveted joint. Thermal distortion in the parts. So is it an advantage of thermal? Does, but it is not less costly. No. Why it is not less costly? Welding has become highly efficient and cost effective now. You have to think that, okay, in case of riveted joint, let's say it is a double strapped riveted joint. If you have a double strap riveted joint, you have two straps. Let's say, why double strap? Double strap, let's say I will say triple riveted double strap butt joint. Triple riveted. let's say you use this to join these two plates. You used triple riveted double strap butt joint. Triple riveted means what? 1, 2, 3 rivets, 3 rows of rivets. Now think of the length of this strap. There is one strap additional you are using. You are having one more additional strap you are using, and width also. You don't know how long. If you are considering this width, then long also. Who is going to give you free? Someone is giving you these plates free? No. So these are the additional cost. Whereas had you welded it, edge preparation and weld it. So which one is more costly? Very clear, right? Okay, we are over here. So okay, thermal distortion in parts. Well, in welding, distortion of the parts may take place. That is a disadvantage of the welded joint. So you have to basically take a due care while the welding process, so that the distortions, that buckling or whatever, that doesn't take place while welding, right? So this is the greatest disadvantage, and this is what he's asking you. No stress concentration problem. In welding, you don't have stress concentration related problem. So this is a relative term, okay? Even if he has used the no stress concentration, even if it is there, it is small, but compared to riveted joint, it is very small. In riveted joint, what you have done is, you have made multiple holes. You have created so many discontinuities in the plate. And whenever there are discontinuities, you are going to have the stress concentration. I hope it is clear now. So this is, so read the statement whenever you are having difficulty in interpreting the इस तरह की statement जब भी आएंगी, sometimes we have difficulty in interpreting. So उसको simple बना दो, तोड़ दो, break it, and then answer that. So that will be good for us. Go ahead. Which of the following stresses are associated with the tightening of a nut on a stud? चलो आप आंसर दो, फिर देखते हैं क्या आता है. Okay, so which of the following are associated with the tightening of a nut on a stud? Stud, I hope you know it, that stud is basically a component which is threaded on both the ends, right? दोनों ends के ऊपर जो है आपने किए हैं, you have produced the threads. Stud में आप क्या करते हो, दोनों ends के ऊपर threaded portion होता है. You are going to have the threaded portion at both of its ends, and one end basically at one end basically you are screwing it into the tapped hole of the larger part. एक part को मैंने उस larger part के ऊपर screw कर दिया, and the other part is coming out, and what we will do, we will allow the other part to go through it, and then we will tighten the nut from the above, right? So one end is always fixed, kind of fixed. I can screw it, but okay, anyway, it is, you have tightened on that particular base, and the other part remains free. So that's what kind of what we call as a stud. Now what he says, that let's say obviously when you will tighten the nut, right? So what is going to happen? Tensile forces are going to be over there, right? The same as bolt and nut, something like when you are tightening the nut, obviously it is going to pull that nut. Oh, sorry, it is going to pull that bolt. Same is going to happen over here. So if we say because of the tensile stresses due to stretching of stud, okay, no issue, stretch hoga wo. Now bending stresses of stud, let's say we are not sure about it as of now, because it becomes difficult at this stage. Sometimes it may happen that you may find it difficult to interpret. You are thinking, सोच रहे हो कि यार ये हो कहाँ, कैसे हो रही है, how it is happening. So let's leave it. We'll come to this, whether it is happening or not. Transverse shear stresses across the threads. ट्रांसवर्स शियर स्ट्रेसेस अक्रॉस द थ्रेड. अब टाइटनिंग तो आप ऐसे कर रहे हो, नट, you're using nut over here to tighten over here. Then he's saying because of tightening across that particular section, shear stresses are going to be induced. ऐसे, no logic. ये स्ट्रेसेस तो इंड्यूस हो ही नहीं सकती. ये हो सकती हैं, they can be, because वो तभी पॉसिबल है when that could not be because of tightening. Keep it in mind. I have two plates and I have joined them. It's something like riveted joint, right? Let's say this is like a riveted joint. If you don't want to consider riveted, I am joining it with the help of a bolt. लो, bolt के साथ join कर दिया. But now if I am applying force this way, I am not applying force. Leave it. What is he saying? Tell me. I am tightening the nut. Let's say, not because of tightening of the nut, this is getting pulled. So if it is getting pulled, it is getting pulled. Okay, that was okay. But he is saying because of the tightening of the nut, it is getting sheared this way also. This is what he is saying. Transverse, perpendicular to its axis. Its axis is this way. Perpendicular to that, transverse shear stresses across the threads. Across the thread का मतलब thread ये है तो across मतलब transverse section में. Is this statement correct? No way. हो सकता है, possible है, अगर मैं इसके ऊपर if I apply a force, that too force if I apply this way. If I apply a force this way, then it is possible. Direct shear. कौन सी shear? Transverse. Then it is possible. But just because you are tightening the nut, this cannot happen. तो ये तो statement अपने आप में गलत है. Right? Torsional shear stress in the threads due to frictional resistance. Obviously ये तो आप समझ सकते हो कि threads हैं, join किए हैं आपने, तो when you want to rotate them, तो threads will slide over each other, तो torsional shear stresses तो exert करेंगे, because nut को जब आप tight कर रहे हो तो torque तो लगेगा ही लगेगा, because of frictional resistance that you are going to have. इसका मतलब है ये statement भी correct है. So I know that 1 and 4 are correct. Right? Give me the answer now. I know 1 and 4. What I know is I know 1 and 4 are correct, but at the same time I know 3 is not correct. I'm not bothered about 2. Let us say I'm not bothered about 2 because I know 1st and 4 are correct, 3rd is incorrect. Give me the answer. You're left out with no choice in this case. That means he has not given you the proper options, but then I'm left out with 1, 4, and I think because he has given all 3 options, so 1, 3, and 2. Now 1, 3, and 2, where is that? 1, 2, and 4. 1, 2, and 4. 1, 2, and 4. So this one. So this is going to the answer. Now you can raise the question, sir. Then is it correct? Bending stresses of stud. Is it correct? I cannot say, because possibility that bending will happen is very less, or there is some kind of misalignment or something. Then if it is leading to the bending, otherwise you don't find any logic that how it will bend. Let's say the same thing. Stud, only difference being that okay, you are having head. In this case also you say that I am tightening the nut, will it bend? Okay, you can say that bending possibility. Okay, if he has thought that way, that okay, while you are tightening the nut because you have a spanner and you have tilted a little bit, so maybe it may bend a little bit. So I think that is what he may have thought. Otherwise, if ideally we think the possibility of bending just by tightening of nut is not there. So let us say if had it been this way, if he had given you the choice, one more choice, let us say he had given you 1 and 4. मैं आपको ऑप्शन दे देता हूं. मेरे पास ये choices हैं सारी, right? I have these choices. I have one choice of 1 and 4. Which one will you choose? Give me the answer. मेरे पास अगर ये choices, I have 5 choices and this is the statement. Now give me the answer. Which one would have been the answer? Right? Then you will go ahead with E. You will not go ahead with this because you have to select the best one out of all these. And the best one is this one. Bending chances, as I told you, just because when you are tightening it, spanner may become get little tilted. Sometimes आपको ध्यान होगा कि आप जब स्पैनर से लगाते हो तो बिल्कुल अगर ऐसे है तब तो ठीक है, बट कई बार क्या करते हो आप टेढ़ा भी फंसाते हो, राइट? tilt, and then you are tightening it. Now this will induce certain kind of bending on this rod. So that may happen. So that is how you have to think. So anyway, I hope you understood. And one more thing, अगर यहाँ पर एक और चीज बता दूं मैं, ये तो केस था, दो तरह की shear होती हैं. When you tighten the nut over here, if I ask you what kind of stresses are induced, you will say tension rod के ऊपर, compression in the threads of nut and bolt, and shear on the threads of nut and bolt. कौन सी shear? थ्रेड्स को शेयर करना बिल्कुल बेस से ये. सो ध्यान रखना यहां पर, यू हैव टू पे अटेंशन ओवर हियर. इन दिस केस बोल्टेड जॉइंट, यू आर हैविंग टू टाइप्स ऑफ shears, and these shears will get induced in different types of loading. नट के टाइटनिंग से तो आपकी ये shear होगी, this kind of shearing of the threads. Compression threads में होगी. This is going to be the compression of the threads also. Tension is going to be over there. Now if I apply external load, this way, then sorry, पहले यही explain कर रहा हूं जो, if I apply load this way, I'm trying to pull it, then this shear is going to be there, and tension is going to be there, and obviously compression between the threads is going to be there. But if I apply this load, then if he is not focusing on the tightening of the nut, नट की टाइटनिंग की बात नहीं कर रहा है, सिंपली मैंने ऐसे लगा दिया इसको फ्री हैंड से. और इफ ही इज आस्किंग द टेल मी द स्ट्रेस इज, देन इट इज वेरी क्लियर, द स्ट्रेस इंड्यूस्ड ओवर हियर विल बी shear. कौन सी shear? ये shear अलग होगी. सो जस्ट डोंट क्रैम द थिंग्स, जस्ट पे अटेंशन कि सिचुएशन क्या एग्जिस्ट कर रही है, व्हाट काइंड ऑफ सिचुएशन इज एग्जिस्टिंग, व्हाट काइंड ऑफ लोड यू आर अप्लाइंग, एंड व्हाट काइंड ऑफ स्ट्रेसेस आर इंड्यूस्ड. ओके, गो टू दिस वन. ये रिवेटेड ज्वाइंट में फेल बाई, आंसर दो. Tearing of the plate at an edge, tearing of the plate across row rivets, and shearing of the rivets. Right? So when you are using riveted joint, so let's talk about this tearing of the plate at the edge. You know, this is the margin area, right? There are two types of tearing failure or tensile failure that we talk in the case of plate. One is कि जब plate को मैंने खींचा, so across the section वो टूट गई at any section, and that section has to be the minimum cross sectional area. So if I am applying, let's say another plate I have joined with the help of the rivet, and I'm pulling this plate, the minimum cross section seems to be, let us say, this one. So it will tear means tensile failure of this plate across the whole section, you can say, because that is a minimum cross section. तो एक तो टेंसाइल फेलियर हो सकता है इस रिवेट का, that is a tearing of the plate across the row of the rivets. Row of the rivets mean basically this is the row of the rivet, another row of rivet, another row of rivet. So this is a minimum cross section area where you have created the holes, so weakest, and therefore it can tear out, or tensile failure. This statement is correct. Another failure could be that if this margin is not sufficient, normally, you know, you give, not always, keep it in mind. Sometimes we say normally approximately 1.5 times the diameter of this. If it is less than that, very small margin is here, then what may happen, and when you're pulling it, so it may tear out from here. ये यहाँ से ही फट गई. Something this way. That means this plate is getting teared away at the ends. So tear away means tensile failure again. So normally that we talk, the failure that or design part that we normally discuss, we talk about the tensile failure of plate across the section. This is ignored, reason being that we take sufficient margin. But this can also happen if margin is not sufficient. So it means tearing of the plate at the edge. ये edge में आपने tearing होगी, इस तरीके से फट गया, यहाँ भी और कहीं भी. So this is also correct. It may fail this way also. Shearing of the rivet, that is pretty simple. Shear तो rivets की होती है. Just take any joint, चाहे lap joint ले लो, whether you take this butt joint or whatever joint, this portion, cross section is getting sheared away. So it means all of these three, they are going to be the answer. So keep it in mind, tearing means tensile failure, but you should have clarity that what kind of tensile failure can take place. Go ahead with this. ये आपकी अंडरस्टैंडिंग चेक करेगा if you have gone through this topic. Okay, you try to answer. Let me just draw the figure. If I can draw it. In a boiler shell, right? Let's say a boiler, you have cylindrical this vessel ऐसे है, और एंड में जो है हमने क्या किया होता है, हेमिस्फेरिकल एंड्स कर दिए होते हैं, राइट? These are the hemispherical ends. Something. This is the boiler shell, right? So in a boiler shell with riveted construction, the longitudinal seam is joined by butt joint. ये बोलता है जो along the length है, ये वाला पोर्शन जो है, मैंने शीट ली और प्लेट ली, and what I am doing is I am bringing them together. अब मैं इसमें यहां पर क्या कर रहा हूं? I am doing the riveting. Now I could have two options. Either you take it or overlap it. तो lap joint बन जाएगा. You can take this and overlap it, do the riveting, or what you can do is you can just take it, fold it, and bring head to head, and now use the straps over it. When you use the straps over it, then it will become the butt joint. So it's your choice how you want to do. But for that, you need to have the understanding, along this length, you have longitudinal stress and tangential stress is acting this way. Tangential. किसी point पे tangential, we call it as a hoop stress. Right? So, this joint, which is longitudinal joint is longitudinal because it is longitudinal along the length. क्योंकि ये along the length मैंने joint बनाया है. This longitudinal joint should be strong enough to carry this hoop stress because this is larger value of stress. तो ये जो joint है, अगर मैंने मान लिया, let's say मैं क्या करता हूं इसको, you are having lap joint and butt joint. You must have the idea that lap joint is not as strong as butt joint. So it means if I have to make it stronger, this joint. So let's say what I'm doing is I'm just overlapping it. मैंने प्लेट को ओवरलैप कर दिया तो आपको पता है एक प्लेट ऊपर है एक प्लेट नीचे है. So when pressure will act, it will try to separate. That means it will try to this way do the shearing. Shearing of what? Shearing of rivets. Now this direction, in this direction, that is this direction, larger value of stress is acting. So if larger value of stress is acting, So I should make this joint stronger. So given the choice, agar lap karu ya butt karu, so which one will you go for? You will say, since the hoop stress is acting in this direction, then instead of making the lap joint, what you do is you do the butt joint, because butt joint is more stronger than the lap joint. So you need to see how the stresses are acting over here. So stresses, hoop stresses are acting this way everywhere. So it means it is trying to separate these two plates over here, or rivets trying to shear the rivets over here. So I will not go for the lap joint. If I will go for the lap joint, it is weaker. And if it is weaker, I am subjecting that weaker one to the largest value of stress. Why should I do that way? That is why. In a boiler shell with riveted construction, the longitudinal seam, हम इसकी बात करें longitudinal seam मतलब longitudinal joint is joined by butt joint. ये statement correct है. Why? क्यों करोगे आप? Butt joint preference is because it is more stronger than the lap joint. So this statement is correct. Let's go to the next one. A butt joint is stronger than a lap joint in a riveted construction. So since butt joint is stronger than lap joint in riveted construction, that is why we are using the butt joint in boiler shell for the longitudinal joint. एंड के लिए नहीं करते हैं हमेशा. यहां पर राइट एक और क्वेश्चन आपका तैयार हो सकता है कि जो एंड वाला जो पोर्शन होते हैं, दो शेल जो यहां पर लगाते हैं, दिस इज द सिलेंडर, दिस बन गया, ये बन गया, और यहां पर भी क्या होगा, एक ऐसा कप काइंड ऑफ डोम I will bring from other side, another dome I will bring from other side this way, and then I will do the prepare the joint at the ends, this end and this end, only then I will have this construction, close end. So in that case, if I ask you which one should you choose over here, क्या करूं मैं, उसको overlap कर दूं कि वहां पर भी head to head करूं और butt joint करूं? Should I go for overlapping or should I bring head to head and do the that is butt joint at the ends? So that you have to see from where? From here. See the direction. Here in this direction, longitudinal value of stress is acting. Lesser value of stress. So if I am overlapping, even if I am using the lap joint, no issue. Because in this direction, the direction in which it will try to come out, the pressure will try to force it out. In that direction, the lesser value of stress is acting, and lap joint will be able to carry that stress. There is no need to bring it butt head to head. But there's no need of doing butting over here and then preparing the butt joint. Lap can be used. So at the ends, we use the lap joints because it has to carry the lesser value of stress. At the end, दूसरे end पे भी वैसे ही करोगे, यहाँ भी. But in case of a longitudinal joint, since it has to carry the larger value of stress, you will go for the butt joint. So the similar kind of question could be prepared for the circumferential. वो joint जो होता है इसको circumferential बोलते हैं. यहाँ पर इसको longitudinal seam बोला. Over there he can call it as a circumferential क्योंकि over circumference you are preparing the joint. So A is correct, R is correct, and R is the correct explanation for the first one. Cold riveting is recommended for fluid. There used to be one for होना चाहिए. Cold riveting is recommended for fluid tight joints in pressure vessels. In cold riveting, there is no application of heat. I think this is a straightforward answer. Nothing special in it. See, cold riveting, we go for the hot riveting for fluid tight joints. Wherever you're going to have the fluid tight joints, वहां पर हम hot riveting करेंगे because pressure जो है वो ज्यादा पड़ेगा वहां पर, because tightening ज्यादा होगी because of cooling action. So we go for the hot riveting जहां पर wherever we want to have a fluid tight joint, we will go for the hot riveting. Let's say ये joint है riveting की. So what happens is at heated state we will heat it, we will do the riveting, and when this rivet will cool, it will exert additional pressure over here, and therefore larger tightening force you will obtain over here, and therefore hot riveting is preferred where you need a fluid tight joint. जैसे आपका ship का hull है, or maybe boilers, because in boilers right now we are not using this riveted joint. Now we have replaced it with the welded joint. But earlier, when you used to have that kind of application, there we used to have the hot riveting. So cold riveting is recommended fluid tie. No, because the tightening you will not obtain that much as you will obtain in hot riveting. So this is a wrong statement. So it means if this is wrong, then only this is going to be correct, because the way the format, this question format is. In cold riveting, there is no application of heat. Obviously, in cold riveting, in strict sense, you can say below recrystallization temperature, but leave it, because that becomes a case or separate case. But anyway, you can say cold riveting means you are at room temperature, you are deforming it. That's all. So in cold riveting, there is no application of heat. Okay, we can consider it as a correct one. So that is how you have to say. I think you must be able to answer it. Which one of the following statements is correct? Anti-friction bearings are. Okay. So these are basically ball and anti-friction bearing is the name given to what? Anti-friction bearing is the name given to ball and roller bearing, rolling element bearings. We call them anti-friction bearing. That does not mean this that they don't have friction, but name given is anti-friction mean that there is a very less friction in case of the bearings. That is why the name given to them is as ball and roller bearing. Journal and this is the same name. Whether you call that as journal bearing or sleeve bearing, we call the same, right? So it hardly makes a difference. So gas lubricating bearing is also something different. You're using the gas to lubricate to create the gap. But anyway, this is simple. Go through this. Okay. So it's a meaning is more or less same. This is how you may have studied that when we define, because stress concentration factor, basically he's not talking about the theoretical stress concentration factor. Reason being, he's talking about the endurance limit. So when he's talking about the endurance limit, it means we are talking about the fatigue stress concentration factor. So loosely, what he has done is, instead of talking about the fatigue stress concentration factor, which he should have mentioned, he simply said stress concentration factor. So basically, this stress concentration factor that he's talking about is KF, fatigue stress concentration factor, and that means component subjected to fatigue. And now, how it is defined? Endurance limit of a notch free specimen. अगर कोई जो specimen है, there is no discontinuity in it. So what is the endurance limit of that? So endurance limit, obviously, if I ask you a question, very simple question, let's say I have a specimen whose endurance limit is this one, right? I have a specimen whose endurance limit is, let's say, 100 megapascal, hypothetically. No notch, no discontinuity. Let us say on this specimen now, what I'm doing is I'm creating a discontinuity. Let's say over here I created a discontinuity. Now I'm testing it. Carrying out the fatigue test. What do you think? Its ability to carry the load for unlimited number of stress cycles without the generation of crack, will that increase or decrease? Obviously that will decrease, क्योंकि आपने once you have created the notch, stress concentration has taken place, and since stress concentration has taken place, so its ability to carry the load, maximum load, will get reduced. So that is why if I will have a specimen which is having no notch and there is another specimen which is having a notch, so this is no notch means no discontinuity, and another specimen who is having discontinuity, so the notched specimen, endurance limit will be less. That is the meaning of this. So Kf is the endurance limit of a notch free specimen, this, that is this value, and endurance limit of the notched specimen, this one. So this value will be more than 1. So I can write it this way. So same way, instead of writing in terms of endurance limit, he mentioned in terms of stress concentration, because in this case, in the notched specimen, you are going to have a stress concentration. So it means endurance limit without a stress concentration. That means endurance limit of notch free specimen. In notch free specimen, you will not have any stress concentration. To endurance limit of with stress concentration, it means endurance limit with the notch specimen, because if you will have notch, you're going to have the stress concentration. So sometimes the statements can be altered slightly. So just keep it in mind. So you should have in your mind this definition and you will be able to answer. So A is going to the correct answer. Go through this one. Wear at outer radius is more than the inner radius when friction lining is new. When friction lining is new, uniform pressure theory is applicable. You know, when the friction lining is new, first wear will take place where? Because when the friction lining is new, this is the friction lining, right? Let us say this is a shaft, this is a friction lining. When friction lining is new, the first wear will take place at the outer. Why? Because you know everywhere pressure is same. When the friction lining is new, everywhere pressure is same, uniform pressure. So you know that wear is directly proportional to PR. This combination you have to know. So you must have studied the uniform wear theory. There you must have seen that this one, that wear depends upon this one, and this should remain constant as per the wear theory. यही तो कहा था, what the uniform wear theory says, that wear is after the initial wear has taken place. After that, this wear, that means PR remains constant. That is how you have said. That is the crux of the uniform wear theory. So it means initially the pressure everywhere is same because lining is new. Then obviously R will vary. So if I ask you where you're going to have the maximum wear initially when the lining is new, you will say, since pressure everywhere is same, then wherever you're going to have the largest radius, at that point you are going to have the largest wear. So initially largest wear will take place over here, and since it is linearly varying, as smallest over here, as R go on increasing, wear will increase. So it means initially something wear will take place this way. Initial wear will take place this way. This is highly enlarged. Keep it in mind. Why? Because radius is very small. यहाँ भी होगी. Over here also it is going to be over there. Something this way. Right? So this was the initial surface. Over here, pressure is everywhere same. Radius is less, so wear is less. Wear means this much amount of wear, axial wear. Here radius is increasing, wear is increasing. This is tilting this way. Radius is increasing, wear is increasing. Radius increasing, wear is increasing. So largest amount of wear will take place at the end. यहाँ से लेके यहाँ तक. Where radius is more. And then the uniform wear theory says that once the initial wear has taken place, that means now you have got a inclined surface this way of the clutch. After that, that wear will remain constant. इसका मतलब wear जो है वो अब ऐसे ऐसे चलती जाएगी, बिल्कुल ऐसे रहेगी constant. At every point after that, there will be uniform wear because of the pressure redistribution. So अब क्या होगा, next stage ऐसे आएगी. So यहाँ भी उतनी wear, here also same 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 wear. That way it will happen, but that is the next step as per the uniform theory. But initially, this is going to be the situation. Now see, wear at the outer radius is more than the inner radius when the friction lining is new. Kyun? This statement is correct because R is more. So it is correct. When the friction lining is new, now see the statement. When the friction, what is the reason why the wear is more at the outer radius? This is the reason. But he has not given you the reason. This is the reason why the wear is more at the outer surface. So he has not given this reason. He has given some other statement. When the friction lining is new, uniform pressure theory is applicable. It's okay. That is correct. So this statement is also correct. No issue. But this statement is not explaining this one. For this statement, the exact reason was this understanding of the wear. Okay, both are correct, but this is not the second statement is not the correct explanation for the. Go ahead. This question is almost on the same line that we have discussed earlier. बस उसको थोड़ा सा उसने कान अलग तरीके से पकड़ दिया और कुछ नहीं है. Component is subjected to a fluctuating stress. A component is subject to a fluctuating stress if the factor of safety based on the following criteria are arranged in ascending order. Now, keep it in mind, he's not talking about the factor of safety that you are applying. We are not applying. See the first question that we discussed. There we talked about what? There we talked about what? When we are applying the same factor of safety, then we were asked to answer that question. That I'm applying the factor of safety, same factor of safety in all the theories, and which one was the conservative? That was the question. Here he's not saying that way. He's simply saying which one is more safer. That is how the interpretation is. So he's saying that which one is more conservative. This is what is. If the factor of safety based on the following criteria are arranged, if the factor of safety based upon the following criteria are arranged, what is the meaning of that? That if we consider from the safer point of view, then which one is more safer? Which is the least safer? Which is the largest safer? Something that way. So that is how. So you already know that this is the least safer, followed by this one. So first is Soderbergh. Sorry, if the factor of safety based on the following criteria are arranged in ascending order. So that means ascending means largest factor of safety you will get in which one? In the Soderbergh. You are more safer. Soderbergh. Then Goodman. Then Gerber. Now see, he has given me Soderbergh 1, Gerber 2, Goodman 3. So you should have the sequence in ascending order. If the factor of safety based on the following criterion are arranged in ascending order, largest factor of safety you are getting on what? You are safe by larger amount in which case? In Soderbergh. So you should go by 2, 3, 1. ये सीक्वेंस होनी चाहिए आपकी, इसने दी नहीं है. 2, 3, 1. If the factor of safety based on the following criterions are arranged in ascending order, it means largest amount of factor of safety that you will get in which one? In which one you will get in Soderbergh? Soderbergh 1, 2, 3, Gerber. So you should be 2 least, then Goodman 3, and then 1. So this should have been this one, 3 2 2 3 1 2 3 1 1 2 3. So I think this has to be little maybe then this statement he is interpreting in a very wrong way, right? If the factor of safety based on the following criteria are used, then it is going to be A. If you say that way, then the factor of safety based on the following criteria are arranged in ascending order. Doesn't make sense. So I think we have to see this one is a this statement may not be correct the way it is represented. Whatever you can just only think this way. We are not applying the factor of safety. We are talking in terms of which one is more conservative. So when you are more conservative, you are more safe. So indirectly, you have a factor of safety in that way, right? So I think it should be the 2 3 1. Otherwise, it has to be reversed if he is talking about the in terms of factor of safety, actual factor of safety. So actual factor of safety, you will apply the largest one in third. Why you will apply in largest one in third? Third one is no way. So then it will be 2. 1 3 2 1 3 2. Then it could be this. So largest if the factors based on following criteria are arranged in ascending order. Largest no, it doesn't make sense. Okay, so I will not go with this this one these options. So as of now, I am sticking to this one. Okay, 2 3 1 because I'm interpreting this line the same way as I told you. So if let me just check it out. Otherwise, I will take this question again and clarify this. But as of now, based upon this statement, the interpretation is that if you go by the which theory is most conservative, then obviously that is more safer. It means indirectly you are more considering the factor of safety. So that means you are more conservative is this one, largest you will get, and this one. So this is how you have to consider. So I will not go by this. I will cross check it again if some options are whether there is a typing mistake or something else. Okay, so just cross check it also in the meantime. But this is how I don't know whether we have made some mistake in kind of typing also. We'll check. But you have to think that way. Okay, now let's go to this one. In fillet weld, this question is straightforward. In fillet weld, throat is pretty simple, I think. Perpendicular distance from the root to the hypotenuse. I think that you can answer very well. So straightforward way. So it is the you have this if symmetrical weld is there, and then in that case you're having this one. So it is this distance. So obviously this is the hypotenuse. If I am having a triangle, these are the legs, and this is the hypotenuse. Then this is the perpendicular distance from the this portion. That is the from the root. For us, root is this. For us, root is this. The point where the intersection is taking place, and from there perpendicular distance. So this is straightforward. Nothing special. Just see this one. When a helical torsion spring is subjected to torque, okay, so basically this is something. This is a helical coiled spring. This is a helical coiled torsion spring. You may have seen it on your those cardboard, like where you have that when you press that cardboard clutch, over there you have this kind of spring. Or you may have seen the hand clutch. If some of you do the exercise, you have a hand clutch. That wire, spring wire is very thick, larger diameter. So when you compress it for the hand exercise, or maybe in the hair clip also girls use, there also you have that kind of spring. So when you will, basically what you're doing is, you're having these ends, you're applying these force over here. So when you're applying, because you're pressing it from here and you're pressing it over here. So basically you are bending it. This wire, whole of wire is getting bent this way. So you are not twisting it. So basically when you're pressing it, basically the bending stresses are induced. For torsion, it should twist. But in this case, this wire will not twist. It will simply bend in this case. So the only stresses that you can talk about over here is when the helical torsion spring is subjected to the torque, the type of stresses induced in the spring wire is tensile stresses, bending stresses, torsional shear stresses, compression stresses. The most appropriate one is going to be bending. Because of bending, indirect tensile and compressive may take place, but the correct answer, the most appropriate answer is going to be bending. Right? Over here also, you will, when you will have this wire, so this is getting bent. So bending stresses are getting induced in that particular spring wire. Which one of the following is known as the maximum capacity bearing? All of you know that right? This is inner race, this is outer race, right? So how do you fill those balls, let us say, inside these races? So you place these balls over here. This way, initially, you place these balls here, and then you adjust these rings. You pull it a little up and then adjust, and then equally space, use the cage and all that. That is how you normally do. But because of this, if you use this method of putting the number of balls between those two races, then the number of balls that can be accommodated are not large. They are limited. Right? So they are limited. The number of balls that you can introduce are limited when you follow this approach. So normally, if you want to increase the load carrying capacity, then what we normally do is we produce a notch. हम क्या करते हैं, जो एक रेस है उसमें क्या करेंगे, slot produce. We will induce a slot over here, right? So this is a inner race. I have my outer race. So here I will induce a little notch over here. So notch means slot. So through that slot, I will just put the balls. So the number of balls that I can put it inside these two races are more, significantly more than the number of balls I can introduce because of through this particular method. And that basically we call it as a, which of the following is known as a maximum capacity bearing. Maximum capacity bearing means we are maximizing its ability of that bearing to carry the load, and that can be done by filling notch bearing. Filling notch bearing, that means here I am introducing a notch in order to increase its capacity to carry the load. Single row bearing, double row bearing, they are the simple classifications, so it is not related to that. Okay, that is how you have to understand this question. So I hope this is a straightforward question, nothing special. These are Mackey brothers, you know. Mackey brothers who carried out the test of friction, and they obtained this kind of curve of variation of this friction with respect to Zn by P, that is bearing characteristic number. Bearing characteristic, we call it as a bearing characteristic. So variation of the coefficient of friction with the bearing characteristic in an hydrodynamic journal bearing was obtained by Mackey brothers in an experiment. And this curve, as you know, this is the hydrodynamic region, hydrodynamic region, thick film lubrication, thin film lubrication, and boundary lubrication region that you know. So this value of Z and P corresponding to the minimum value of friction that they obtained, that what value of this parameter we have, which will give us the minimum coefficient of friction, that value of Zn by P, we gave it a name called as bearing modulus. So don't get confused with the Mackey number. Mackey brothers basically conducted. Mackey brothers basically conducted this experiment, right? So this number, this value of Zn by P, we call it as a bearing modulus. Okay, that is how you have to go ahead with this. So I think you may have remembered this definition, so you will be able to answer. So I will not go into detail, but basically, what is the basic load rating? We also call it as a dynamic load carrying capacity. Dynamic load carrying capacity. That the constant load in radial bearing or thrust load in thrust bearing, that 90% of the bearing, a group of a bearing, can carry for a rating life of 1 million revolution, right? So that is what before the appearance of first fatigue crack. That is how we define. So this is the definition part you should remember. So then let's go to the next one. Which aspect is not true for subtooth when compared to full depth system? Stub tooth, that stub tooth is nothing but so stub you should remember from the stubble. किसी चीज को हम थोड़ा सा काट देते हैं ना, from its original length, height or whatever, we call it as a stub. Okay, जैसे अगर आपने ट्रिमिंग की, जैसे दाढ़ी की, so obviously what we are saying stubble. ये जो छोटे छोटे बाल बचेंगे ट्रिमिंग के बाद, we call them as a stubble. So same way, if I am having this particular gear tooth, pressure angle same है, let's say even for the same pressure angle, what we can do is जो addendum है, we will make that addendum short. ये value we will make it small. So if I have a something this way, so what I did is I made it little small. Stub tooth बन गया है. So even though the pressure angle of that system is same, but what I have done is ये addendum portion जो है I have made it a little small. You would have various reasons for making that, but what do you say? Which aspect is not true? True क्या है फिर? Working depth is about 20% less. Working depth अपने आप ही कम होगी because this portion you have reduced. So obviously this is true. This is true. Addendum is made shorter. I have made addendum shorter by a small amount. This is also true. More interference. Now interference will come when that tip will dig in that particular non-involved section of that other mating gear. So rather आप क्या कर रहे हो? वो tip को ही कम कर रहे हो. You're reducing that particular more portion. So rather it is not increasing the interference. It will be decreasing the interference. So not more interference. Less interference should result when you are having this one. So ये भी correct statement है. Tooth becomes stronger. Not true. Right? So working depth is 20% less. This is okay. Addendum is made shorter. Okay. Addendum आपने shorter किया, वो भी ठीक है. More interference should reduce. Tooth becomes stronger. Why the tooth should become stronger? There should be logic. Tooth stronger मतलब teeth का size बढ़ रहा है क्या? And tooth का size we measure it from there. You know how stronger the tooth is, we calculate from module. Module has decided the width of the tooth, and that width of the tooth is at the over here pitch circle. So that I am not changing. So tooth becomes stronger. I have no logic why the tooth is becoming stronger by doing that way. So this statement is not correct. So, right? So this is going to the answer. Not true. This is not true. For the tooth to become stronger, either size should increase or something which is not happening over here. Clear? That is how you have to answer this. Go to this one. Tooth profiles must not have excessive contact stresses as determined by the wear load to ensure durability of a gear pair. This wear load is obtained by using what? Give me the answer. You know it in gear design, spur gear design. Some more answers? Okay. So tooth profiles must not have excessive contact stresses. You know, we design the gears, very basic calculation that we talk about at your level is that one we design for the wear strength, the other one is the what? Beam strength. Beam strength is for bending. Wear strength is the surface fatigue failure. Wear strength is the surface fatigue failure. Because of the repetitive stresses, दो सरफेसेस आ रहे हैं, रोल कर रहे हैं, दबा रहे हैं और वापस जा रहे हैं, घूम के गया, again it is coming, compressing, rolling, compressing, going, and that cycle continues. So it's a case of dynamic loading, fatigue loading. So because of that, surface fatigue failure takes place. Surface के ऊपर cracks develop होंगे, minute cracks, they will come out, pitting failure will take place. Now, for that, you have this wear strength. And in this case, you know, surface endurance strength का जो stress formula में that surface endurance strength का concept भी आता है, if you have little idea. But anyway, leave it. So it means, what is this wear strength? Wear strength is the maximum value of the tangential tooth load. ऐसा क्या लोड है tangential tooth load? Obviously we're calculating at the pitch point that I can apply on this gear tooth so that wear failure, surface fatigue failure. Wear means surface fatigue failure should not take place. That means that crack should not get generated at the surface and it should not come out in the form of very small chips. We call it as a pitting failure. गड्ढे हो जाते हैं छोटे छोटे surface के ऊपर. So wear over here is not the wear that you think in a normal sense. Wear you think that okay, abrasion, छोटे छोटे particles निकलते रहे, निकले कैसे? So over here we talk about the compressive. So this equation was basically given by the Buckingham. So basically this equation is the wear load to ensure durability of the gear plane. Basically wear strength equation you can say was given by Buckingham, and this wear strength was based upon the Hertz contact stresses theory. Hertz जो था, this is an investigator, he has done a lot of work on the contact stresses. When two surfaces compress against each other, then what actually happened and how does the stress distribution is there and how those surfaces can fail and all that. So he has done a lot of work in the contact stresses. Contact means when they're compressing against each other. Making that basis, Buckingham ने क्या किया, उसको बेस बना के this equation दी. This equation was given. Wear strength. So wear strength is nothing but the maximum value of the tangential tooth load that gear tooth can carry without pitting failure, surface fatigue failure. ये ध्यान रखना. So Buckingham ने दिया हुआ है. ठीक है. Lewis तो आपका बेंडिंग की है. बार्थ फॉर्मूला ने तो बार्थ ने केवी फैक्टर दिया है. जस्ट सी ओवर हियर. बार्थ ने केवी दिया है. Contact stress at the wear load to ensure durability of the gear. The wear load is obtained by using. हाँ ठीक है. Wear load का पूछा. मैं I wanted to cross check कहीं ऐसा तो नहीं है वो contact stresses की बात कर रहा है, ये भी ध्यान देना. So he's not talking about the contact stresses. He's talking about the wear load. ये. So wear load जो Buckingham. And Buckingham भी दो equation because in gear design दो जगह पिक्चर में आता है. एक आता है effective tooth load bending में, where we divide PT by KV. KV Barth formula, KV की value has been given by the Barth. 6 divided by 6 plus V, if you remember something, 3 divided by 3 plus V something. That is one way of calculating this effective load. Another way of calculating the effective load is tangential tooth load plus dynamic load. Separate dynamic load. That was also given by the Buckingham. So in two places, Buckingham will come into picture in this design part. One is while calculating the bending stresses, this effective load over here. And other one is this equation which is in wear. हर्ट्स का रोल के हर्ट्स ने तो केवल कॉन्टैक्ट स्ट्रेसेस, ही हैज डन द वर्क ओनली इन द कॉन्टैक्ट स्ट्रेसेस, वो आपके दिमाग में रहे, दैट्स ऑल. जस्ट व्हाटएवर आई जस्ट मेंशन्ड ओवर हियर, ये क्वेश्चन उसी के बेसिस पे है. We get the power, you know, while I'm transmitting power, I have 2 pi nt torque divided by 60, right? Let's say units mein. And what is torque? Torque जो है वो tangential tooth load into radius of that particular pinion or gear, whatever जो आप बात कर रहे हो. अगर if this is pinion, speed of pinion, then this is radius of pinion. If this is gear, then this is gear. वो आपके ऊपर है. PT is the tangential tooth load. At pitch point, you know, line of action, and at pitch point, this component is PT, tangential tooth load, at pitch point. So, PT into R, pitch circle hai, this is pitch point. So, obviously, this is PR, whatever you are having till this point R. So, this becomes the torque, PT into R. So, basically, depending upon the power that I am going to transmit, I can get the value of the tangential tooth load. कि कितना लग रहा है. अगर मैंने 100 किलोवाट और 10 kilowatt power transmit करनी है, let us say if I want to transmit 10 kilowatt power, then to transmit that power, how much force is getting applied tangentially at the pitch point, वो ये है. So this force you got it from the power. इस equation से आपको मिल गई, right? Got it from that equation. But is this the only load which is acting on the gear tooth? क्या गियर टिथ के ऊपर पावर ट्रांसमिशन के कारण जो लोड लग रहा है वही है? Is the load which is acting on the gear tooth is only just because of this power transmission that is taking place, or is there any additional load which is acting on the gear tooth? इसके अलावा भी कुछ additional load लग रहा है, some more load is acting on that gear tooth. So this is more or less like on the static conditions. बहुत ही low speed की बात करते हैं हम, almost static conditions की बात करते हैं, that this is the force that will be acting. In addition to it, there are other loads which are acting on the gear tooth because of so many practical problems or that situation that you have. For example, if you don't have contact ratio proper, then impact load can take place. So some of the reason he has given you over here. For example, we understand that, let's say I will go one by one. Inaccuracy of tooth profile. We are assuming that you have absolutely perfectly manufactured that profile, involute profile. But is it possible for you? No. Inaccuracies in gear tooth profiles may take place. Inaccuracy means the curve that you have obtained, is that curve perfectly what you have designed, or is it deviating from that? If it is deviating, you're going to have a trouble. Or errors in tooth spacing. Tooth को जो दोनों तरफ से आपने when you bringing them together, there's a spacing errors. Or maybe misalignment between bearings. The shaft on which you have installed that particular gears, now you are supporting them on the bearings. So bearings over here, there is a misalignment. So basically what is happening is this power that you are talking, force that you are talking about, that is based upon the ideal conditions. But actually, because of these errors, additional load will be acting on the gear tooth if any of these inaccuracies come into picture. और इसको अगर आपने सोचना है तो इस तरीके से सोचो, that is something like it had to come in contact smoothly, but it didn't come smoothly in contact, and therefore some kind of sudden load that acted at minute level, at micro level, and that load is impact load, you can just think of, and we are calling it as a dynamic load, and that dynamic load can come into picture because of any of these factors. So these all factors are responsible for that. Okay, so इसका तो आंसर हमें पता चल गया, but how to account for that, I think maybe next one or two questions में मुझे शायद हो सकता है similar lines पे question frame हुआ हो. Now if I want to find out how much is the actual load acting over here, so we call that actual load as effective. Although effective load, that effective load is not PT, that is more than that. If it is 100, so is the actual load 100 only? You will say no, some additional is acting because of these factors. How much is that additional? So you have two ways. One is, जैसे मैंने last वाले question में बताया था, लिखा था, what I wrote over there, kV. So I will take this particular velocity factor value kV which is less than 1, क्योंकि ये value was, if it is less than 1 then obviously total value will be more than this. This is one way of doing. एक और तरीका है जो मैंने बताया था, इफेक्टिव इज इक्वल टू विच आई रोट ओवर देयर बकिंघम इक्वेशन एंड ऑल दैट. क्या करो, दिस इज एक्टिंग एंड इफ यू कैन कैलकुलेट सेपरेटली दैट एडिशनल लोड. क्या आपने बोला दो इफ दिस इज 100 किलो न्यूटन एंड इफ यू आर सेइंग बिकॉज ऑफ दिस फैक्टर 5 किलो न्यूटन एडिशनल लोड इज एक्टिंग, तो क्या करो, ऐड कर दो. You should have the method to calculate that. If you have the method, then your job becomes easy. So let us say that is PT plus that additional dynamic load. We call this that PD. So 100 plus some additional load. This is another way. So I want to find out the actual load that I can find out from this way or this way. And ये जो मैं बात कर रहा था वहां पर लास्ट में मैंने कहा था, बकिंघम ने एक इक्वेशन, बकिंघम has given one equation where you can find out this additional load separately and then add it to this load to get the actual load. Okay, so I hope you got it. So as per this, I think we will go by 1 2 3. So all the options are correct. Go through this one. Both these things I have discussed with you in separate questions. What am I writing over here? Beam strength, wear strength. Beam strength आपने कहा 100 Newton. This you said 70 Newton. This is the maximum tangential tooth load. Beam strength is maximum tangential tooth load that your gear can carry without bending failure. तो बोलता है अगर if I will apply 100 Newton, this is the maximum load it can carry without bending. Failure नहीं होगा, 100 तक ले जा सकता है. It's okay. But you also have to check for wear also. So wear strength we discussed. What we said? ऐसा load that again same concept. What is the maximum load, tangential tooth load that I can apply on the gear tooth so that surface fatigue failure does not take place. वो pitting जो गड्ढे जो create होने हैं that they should not develop. तो ऐसा maximum load क्या है जो आपका gear tooth carry कर सकता है without pitting failure. So let's say I have taken a hypothetical value. It may be more or less, I don't know. But anyway, let's say this is 70 Newton. Now, tell me the actual load that I will apply. The actual load or effective load that I should apply. What should be that load so that you are safe in this and you are safe in this also. So you will say that if P effective, the actual load hai, the actual load that I am applying, if it is less than this, then I am safe. कोई दिक्कत नहीं है. But this effective not only should be less than this should also be less than this. So the actual load that I am applying, if it is less than this as well as this, then I am safe because I will be safe in this as well as I will be safe in this. But if actual load is more than this, but it is less than this, it will fail in this, right? So for me, for the safer design, what is the condition? Actual load should be less than this. Now see the beam strength is the maximum value of the tangential tooth force that a gear tooth can transmit without bending failure. This definition. For safe design of gears, beam strength should always be more than wear strength. Is it correct? For safe design, this should always be more than this. ये होना चाहिए क्या? यस, हो सकती है, ये कंडीशन भी हो सकती है कि फॉर सेफ डिजाइन बीम स्ट्रेंथ शुड बी ग्रेटर देन वियर स्ट्रेंथ. That condition should also be fulfilled, because अगर बीम स्ट्रेंथ इज लेस देन वियर स्ट्रेंथ इज मोर, बट वो बेंडिंग में फेल हो जाएगा. वियर तो तब आएगी जब बेंडिंग से बचाओगे. So this statement is also correct that way. So we can say this statement is also correct. But is it the explanation for this? Beam strength is the maximum value of the tangential force that can gear tooth can without bending failure. Okay, statement है. पर ये क्या इसकी explanation है? No. So independently both the statements are correct, but this is not the explanation for this. Okay. So this is how you have to see. ये additional part जो मैंने आपके साथ discuss कर लिया. This I discussed with you. I think this is the Lewis equation that you may have studied. So what it says, if you can recall, it assumes that whole of that total tooth load is assumed to act. The whole of that gear tooth load is assumed to act at the tip. So when you are carrying out the beam strength analysis, so he is assuming that this PT is acting on the tip of the gear tooth, and then he is carrying out the bending failure analysis. But actually, jo PT means FT, whatever you are saying, FT. So in the formulation of the Lewis equation for the tooth gearing, it assumed that tangential tooth load FT acts on कहाँ पर act करेगा? तो pitch point, tip of the tooth, root of the tooth, face of the tooth. So tip of the tooth, obviously at the tip of the tooth. So he assumed it to be acting at the tip of the tooth. पर एक ध्यान रखना आपने इसमें, when we are calculating the value of PT or FT, that is at the pitch point. Calculate हम pitch point पे करते हैं because it comes from the power equation, right? If you see, ये what I told you, this is the line of action, right? Pitch point ये है, this is the line of action, and its component is PT, and this is R, pitch, radius of the pitch circle from here to here. So if power is given to you, I will calculate the PT. So basically, when you are calculating the PT from the power equation, you are calculating this tangential tooth load at the pitch point or pitch circle, pitch point more appropriately. But when you are carrying out the bending analysis, he assumed, he, not me, he, who? Lewis assumed this force to be acting at the tip of the tooth over here, and it is distributed entirely over here, right? तो ये difference आपको clear पता होनी चाहिए कि what is the meaning of this acting at the tip and from where normally we calculate this value. वहां कंफ्यूज नहीं हो जाना कि यहाँ पर टिप पे लग रहा है और कैलकुलेशन में इसके बेसिस पे करूं कि इसके बेसिस पे करूं. कैलकुलेशन यू हैव टू कैलकुलेट इट फ्रॉम द पिच पॉइंट बेसिस ओनली. Go ahead. Walls factor takes into account consideration of the effect of what? Right? So if you, I think, I don't remember that formula now exactly, but if you see the helical, you can cross check it, but I think this is how I'm recalling. इस तरह कुछ मैं recall कर पा रहा हूँ. And so in springs, basically, close coiled helical springs, when you are applying the force, then you are having stresses over there, which are induced. One is torsional shear stresses and direct shear stresses. So there is one factor called as Ks that takes into account the factor of direct shear. And then later on, walls give you another factor, taking into fatigue into consideration. And he gave this value this way, pi dq. So he modified this formula. He modified formula, not formula, or you can say instead of this Ks, he replaced it with the Kw. So we call it as a Wall's correction factor. And that basically took into account the curvature effect. Curvature effects mean that when the spring will be subjected to dynamic loading, even though spring wire is of ductile material, but because you have a curvature means, just have a look over here, my hand. So when you are reducing the radius of this particular portion, now what is happening is kind of discontinuity is getting formed. and that is, we call it as, because of that stress is getting concentrated over here, and we call it as a curvature effect. So more I'm doing it smaller, something this way, so greater the curvature effect, greater the stress concentration, and therefore I have to use the sum factor in order to account for that, because the stress will increase. So this will not take into account this Wahl's factor, basically consider this as well as that stress concentration effect. So that is why if you see over here, Wahl factor takes into account consideration of direct shear stress, stress concentration factor, direct shear stress. This was taking only direct shear stress. So this not only take direct shear stress, but stress concentration effect also, or curvature effect also. Stress concentration due to curvature. So not only this, but this also. So basically, Wahl's correction factor takes into account both of these effects. This was replaced by this. This was for direct, and in addition to it, he is taking the stress concentration effect also into account, curvature effect. Okay. So this is the last question. I think this one I just explained to you. Sorry. Helical spring. Compressing. I think this is the same thing he's saying. Helical compression will be subjected to axial load P on the plate connected at the end of the spring. The spring will be subjected to what? When you will compress it, actually, this is how we do this analysis is done this way. So basically, we are bringing it this way. So when you are applying a force over here, what is happening is, when you're bending over here, this is the coil diameter, this is the force, so movement. So over here, this one is basically getting bent. This is bending, but this wire is connected, so it will try to rotate the wire. So if you see, the wire over here will be rotated this way. So even though यहाँ पर आपको bend हो रहा है वो, but because this wire is twisted this way, that when you will, this portion will bend, it will try to twist that wire. It's something like saying that if I'm having my hand over here, if I will apply a force downward, what is going to happen to this portion? The same thing. So I'm applying a force downward, so it is, this portion is bending downward, but this portion is trying to rotate this, my arm, this portion of the arm twisting, that means twisting. So same is happening over here. This is going down, so it is getting twisted. Same is happening down there. The whole of the wire is getting twisted along this whole of this particular length. So one is torsional shear stresses on the wire, and also because the force is transmitting across any particular section of that particular coil, so direct shear stresses will also be acting. So over here, if you see, not only torsional shear stresses, but this answer should be D. Torsional shear stresses because of this twisting, and since you are applying the force downward, that direct force is also crossing across that particular cross-sectional area of that particular any wire this way. So direct shear stresses will also going to be induced. Okay. So that is all. I think we covered almost 30 questions. That is what we were supposed to do. So I hope you enjoyed this session. So maybe let's see if we will come out with some more session on this or not. We will plan it. So see you in the next session. Till then, bye. Thank you.